All right, our last speaker for this session is Dave Rudolph, and most important thing to know about Dave is he's not from Imperial College. He's from Earth and Environmental Sciences, University of Waterloo. And Dave, you're going to tell us a little bit about how to protect our water supplies.
Thank you, Lee. Yeah, the two things you'll notice right away about your last speaker is, first of all, I have a relatively strange accent because I come from the colonies. So I'm from Winnipeg, so a little bit different than the other three. And also, I only got to meet and get to know Howard over the last few years. And as being sort of the token, somewhat tolerated regional hydrogeologist on committees, sitting around tables chatting, but in that short period of time have found a new friend and colleague, and it's been a wonderful ride, Howard. Very, very great. So what I want to do our last talk on this afternoon is a topic I've been struggling with for quite a few years with a colleague of mine, Professor Emil Friend. Many of you will know Emil. And that's looking at how public supply wells are quantitatively looked at from a vulnerability point of view. And overall, I want to kind of look a little bit back on where we've been and where we're going forward a little bit on this. I think there's been some great progress and lots to do. But just to get started here, here's a small little quote that comes from a paper that Howard and Pat wrote a few years ago on water security and the science agenda. And in that, there was a little quote saying the freshwater environment is facing unprecedented pressures in the Anthropocene, the newest geological epoch, marked by profound human influence on natural systems, something I think we can agree with. And that paper, I have my students in my grad class read as their first start to the class, and then I ask them, based on this agenda, where are we going in hydrogeology? Where is groundwater moving now forward? So I asked them that question. So just as a little retrospect, let's take a little look at where we've been. So the first part here, we spent an awful lot of time looking at water resource development. There I am sitting beside my very first flowing artesian well. And then as time went on, people realized that groundwater was quite susceptible to contamination. And once it got contaminated, it was very difficult to deal with it. Tools that developed along the way were numerical models, of course, that we've talked a lot about today, and of course very useful in the groundwater world, and I'm just not sure if that's Eric Wood or not, but working away on an analog model, which was a phenomenal tool back in those days based on capacitors and resistors and electrical flow systems. And of course, they've been now replaced by super advanced numerical codes and tools that we all have the benefit of using. Then, of course, as time went on, we started focusing on solving the problems, and remediation became a big topic through the 90s. And then, as we've talked a lot about today, the groundwater-surface water interaction, the merging of the water cycle, has required us to look at this in a lot more detail. There's some tile drains coming out through this agricultural field into a lateral drain going down to a main river. So then the question is, where are we going from here? And I would argue that all of the things that if I can back up here, all of the things that we've learned through this cycle are kind of getting us back to this component of resource development and management. And I want to look at it from the point of view of wells, public supply wells. So I'm using some statistics from our neighbors to the south, often have very good data sets. This is relatively fresh information. So something like a third of the population of the United States depends on groundwater from a public supply well on a daily basis. So you can imagine then that the health and welfare of these people really depend on this quality of this particular resource. But when you look at it, over a long period of time, the infrastructure is aging rapidly. So many of the wells that have been drilled for 50, 60 years ago, sometimes longer, they've been pumped for a long period of time. So that has a real significance in terms of them capturing legacy contaminants, which I'll show you in a moment. The other thing, interestingly, when they did this study, it was kind of a shock that 1 in 4 of these wells exceeded one of the drinking water standards in something. Could have been a variety of different compounds, and maybe many. And as we've heard, of course, over the last day, projected significant increase in demand moving forward, and in an urban environment, probably turning more and more towards groundwater as that source, as surface water sources are overexploited and less able to withstand the change with climate. So when one looks at public supply vulnerability, you normally think about it in 2 different categories. One is how they're exposed to a chronic degradation, so over a long period of time. And the reason for that, of course, here's our receptor, our well in the ground here, slowly converging flow towards it, and anything that happens to be within its zone of influence here, this is sort of thinking of this as an urban area with gas stations and maybe dry cleaning units and a landfill and a graveyard, sitting inside this area of capture, and then underneath it, slow-moving contaminants emanating from those sources finally arriving at the well, resulting in a very complex mixture of potential contaminants and a real difficult problem as to how to predict it. So an example here in cold regions, and many of us work on this problem, is the buildup of road salt. So salt itself, of course, is very difficult to treat, expensive to treat, and this is a typical response over a period of time. This is back in the 70s, one of the well fields in Kitchener-Waterloo, and here's the threshold of interest, the drinking water limit, and these wells starting to exceed this. So if you're a municipal purveyor of water, you're really concerned about, first of all, when is that limit going to be breached? What's that final concentration going to be, and what can you do about it? So you're going to build infrastructure to treat this. You're going to have to manage the wells or maybe change the wells. So all of this is happening over a very long period of time, getting back to the point that these long-term groundwater supply systems are aging. The second part of it is more of an acute degradation. So this is something that would be more event-based. So in that scenario, we're mostly talking about pathogenic contaminants, so human enteric virus, protozoa, bacteria that could cause illness. Now, so these are, of course, colloids, living colloids moving through the subsurface, a different type of thing than salt, for sure. And the way this has more or less been approached has been the realization that groundwater and surface water being connected, surface water sources are quite frequently areas where pathogens can reside and are high concentrations. So here's an example, one of the sites we're working away on. Here's a public supply well right next to a stream. It's in flood stage. So in where we live in the northern cold climates, snow melt that occurs as real rapid inundation and flushing off the agricultural fields and the urban areas into streams, running right by public supply wells, causes a temporary increase in risk, something that's, again, very difficult to track. With the increase in variability in climate, we're seeing more of that. For instance, in Kitchener-Waterloo, we had 3 midwinter melts this year where the entire snowpack melted and ran off. And then it was cold again. It infiltrated into the ground and froze, and we had this frost pack build up with ice in it. So it completely changes the dynamics as a result of this climate change. Sort of, let's say, variability in climate, however you want to think about it. So over the last 3 or 4 decades, the way we've kind of approached this problem has been to try to delineate the areas that are providing water to a specific well. It doesn't have to be a large municipal production well. It could be a small one for a small village, whatever it happens to be. Or it could even be a small well in a farm where you're worried about whether a septic bed is within the area of the capture of that well. And what we've done is more or less used numerical tools to delineate these areas. And that's primarily because it's almost impossible to ground truth them. You can't measure them in the field very well. So we used analytical models for many years, and then, of course, with the advent of much stronger three-dimensional models, we've been able to do lots more with it, using techniques like particle tracking, I'll show you in a moment, provides us with an opportunity to determine what part of the land surface is likely the most at risk, where we would look for sources of contamination that would infiltrate into the ground. And beyond that, we can even try to determine some time of travel. So this gets to Jeff's points this morning about learning about groundwater age and how fast groundwater moves. So just a little example, which I'll use for a couple of points here. This is where I live in Waterloo, Ontario. We draw water primarily from a thick glacial drift sequence that's a mixture of till units and sand and gravel units, quite a complex interaction of sand and gravel units with till between them as aquitards. So you can more or less make them out here. So in this particular approach, what we would do is develop a three-dimensional flow model, calibrate it as best we can, and then at the well field here, we invert the velocity field so that now it's moving in the negative direction, release virtual particles from the well, and let them migrate through the subsurface. So as they do that, they're moving through the advected flow field. You can march them along for 1 year or 10 years or 100 years, or let them run out to steady state, and then you can track where they are. And that provides you with a way of getting times of travel maps and capture zone maps. So that's a pretty routine way of doing this. So you'll end up with a map something like this. Here's the production well, there's a stream next to it here, and here's a little farm. And in this particular case, this septic weeping bed is not sitting inside the capture zone of that well, so it's not a target or a concern as a risk for that particular well. So that's pretty good in terms of getting an idea of what's important and what's not on the ground surface, but it doesn't tell you anything really about the concentration distributions. So this is something, of course, if you're a municipal manager, you'd like to know. So let me propose a different approach to this that we might be able to sort of enhance our way of dealing with quantitatively evaluating it. So what I propose here is adopting something Emil developed some years ago in fact, solving the advection dispersion equation in an inverse method as well. In other words, instead of injecting particles, inject solute into the subsurface. So calibrate the model again and then run in a transient time period the solute transport code. So what this does essentially is replaces the particles with solute, let that move through the subsurface, and now you can incorporate dispersion, attenuation, mixing, all of the things that would change the concentration of that contaminant as it migrates. This, I think, would significantly enhance the assessment of the vulnerability mapping. So let's just look at this again. These are the particles released. In this particular case, this is 40 years. So if you look through the subsurface here, you would project it to surface, and it would give you an idea in 40 years how long anything within that area would be captured by the wells. If we run it right out to steady state, in this case it took almost 300 years to reach that, and that's all the particles making it to the surface here through this complicated system. So you can do the same thing by injecting solute mass. So in this case now what we're doing is inverting the flow field, running the advection dispersion equation in reverse, and now we've got a map essentially of the probability of capture within this area. So it provides a lot more information, the same as the particle tracks would, but a little bit more detail. And there's the cross-section through the 40-year scenario. One other thing we can think of then is imagine if we went within this area of influence and each one of the nodes that are part of our numerical model, we release a pulse of mass and let it migrate through the system here. I'm going to borrow this because I think it's a little bit stronger. So we release a pulse at one of the nodes and let it migrate and capture that breakthrough curve at the well. Now, as it breaks through then, what you'll find is that might be the threshold that you're interested for that contaminant, and there's the time it takes to breach that threshold point. Then it's migrating through advection dispersion. There's its maximum peak, and there's the tail. So we end up with an indication not only of the arrival of the front end of the contaminant plume, which may be years in front of the advective time period, and we get an idea of how concentrated it is. If it's far enough away, it will have diluted enough not to be important. So by doing this type of assessment, we can get to the expected maximum contamination, how long will it take to reach that value, where is a breaching contamination, and of course, how long will we be exposed to it. So then our little maps start looking like this. So you can imagine if we had a case here that we're worried that maybe this is a new plant we're building here or an old site. And by running it at each one of these nodes within the finite element grid, we can contour it up and have an idea of what that maximum concentration would be should the spill occur at that point. In this particular case, how long it would take to get to that maximum. This is a case we applied it to. what the time to the threshold would be, in this case, of course, 10 years less than the center of mass arrival, and then how long it would be exposed for. So you're essentially building maps that give you much more insight than the particle track would. So that's an evolution that we might work towards in terms of the chronic problem. And the second one I wanted to look at here is how do we manage this acute problem? So here's the typical term we hear about groundwater under the direct influence of surface water, or GUDI being the acronym for it, mostly focused on pathogens. Okay, so, and the thing about the complexity here, of course, is that the pathogens themselves are subject to filtration, predation, they die, they're colloids migrating through the subsurface. So depending on where you are in Canada, the United States, or different parts of the world, people try to come up with ways of suggesting how long of a travel time do we need, but, well, that will ensure protection so that these particular processes will annihilate the risk of that pathogen. So there's a sort of scenario here with leaking underneath the surface water body and being captured by our well, and that, of course, surface water body being influenced by the land use around it. So these time periods, although they're somewhat arbitrary, are based on best guesses and some assessments in the field, but not necessarily incorporating all the physical conditions. So this became very obvious to us in Canada back a decade and a half ago. Probably the most influential event in terms of groundwater and source water management that's ever happened to us in Canada was a tragedy that occurred at a small town outside of Kitchener-Waterloo called Walkerton, where we had a sort of a public supply well sitting at the edge of town here, right next to an agricultural field, happened to be a livestock farm. We had a massive precipitation event that occurred in the springtime, just after the snow melted. The soil was still relatively frozen and wet. The farmer had just applied fresh manure on the fields, and this storm occurred. So what happened here was, and coming back to Jeff's comment about microtopography, is that temporarily a small body of water formed next to the public supply well. No other surface water bodies around it. Whoops. And so the concern was then, how would this influence the well? Of course, what the disaster for that is, look at that, flashing on and off like that. That's a pretty good trick. But of course, the disaster as a result of that was 7 people died from this outbreak, almost 2,500 people seriously ill, and that forced the government to completely rethink how source water is managed in our area, looking at from a watershed point of view, invested huge amounts of money, redeveloped our provincial framework. Of course, in this particular case, as a result of a E. coli that was a very deadly strain that was released into the system. So the question came down to the point of saying, what really is the quality of these types of runoff waters in the springtime, and how does it get through this subsurface? This infiltration dynamics, this represents an area of very challenging research and try to figure this out. So we went back into the field to look for this type of scenario elsewhere, and sure enough found it in so many different locations. So here's another well field. This is the town of Woodstock. Their wells are sitting down in this woodlot. These blue lines sort of represent ephemeral streams that form during the snowmelt. So this water now is flowing from a very large catchment area down through these small rivers down towards the well field. So capturing and bringing water from a long way away right up to the wellhead, and then infiltrating. And the question is, what's the quality of this water? So in testing it, Mike Christie, a master's student of mine, looked at this in detail, measured it to find that it was relatively low in concentrations of chloride, quite dilute in terms of nitrate, running off agricultural fields here. But in looking at the microbial results, in terms of microbial indicator species for pathogens, extremely high. So this is very rich contaminant water flowing right now down towards the wells that are sitting in the field here. So that time of travel you're expecting for 90 days, you're totally losing out. Last 3 slides. So in order to evaluate that subsurface flow system, we made use of some new technologies. This is a tension infiltrometer that allows us to infiltrate dyes and these microspheres down into the subsurface under tension. So letting it actually release down through the farm field and migrate down through the process. So there we are, releasing it, then coming with a backhoe and digging the front end of it out. And I wanted to put this in, Jeff, to show you there still are students that work out there in the field. Here's one of them, digging away, and then seeing how that dye looks as it migrates its way down through this macroporous overburden right towards the top of the bedrock. And here's Joanna picking away at the profiles here to look for the microspheres, and sure enough, detecting them all the way through the profile, infiltrating rapidly down through this material under tension, which is the really intriguing part of it. So that, of course, showed us that was possible, the migration of these colloids moving through the subsurface rapidly. So I think our evolution as we move forward now is going to be that I think we can enhance the way we look at wellhead protection. We need to include uncertainty. We learned a lot about that over the last couple of days. I think there's great ways to do that. We need to be incorporating more of these event-based threats for security to our public supply wells. GUDI needs to be rethought and reevaluated, which is under the process of that, particularly in cold regions like we live in here. Learning how pathogens move through the subsurface as colloids, very challenging issue, particularly through frozen soils, which is another topic we're working on. And then the final one, which I think our Global Water Futures is really going to be looking at, is how do we take all of this new thinking about protecting public supply wells and apply it to the most vulnerable communities. So the First Nations areas that we've been working on, places around the world where I think our new sensors that are going to be available for almost real-time detection of pathogens, communication data for early detection and prevention will take us an awfully long way along that road. And with that, I'll thank you very much for your time.
Dave, that was really interesting. One concerning finding in Scott Giuseco's paper that came out last year with the fossil water was that half of the wells that showed fossil water, ones below 200 meters or so, half of them had detectable bomb tritium, suggesting that they're vulnerable to modern contaminants potentially, even though it's fossil water. We weren't able to come up with any mechanisms. We weren't sure if it was well completion, preferential flow. I just wonder if you had a thought on, I don't know, if you have a hunch that this is perhaps more widespread than we might otherwise like to think.
Well, so a really good point. And the fact that the tritium shows up in the deep environment there gives you an indication that at least it got down there since the 60s, probably. So there's at least a component of water down there that's relatively young. People have pointed at the fact that the casings are leaking, and if it isn't this casing, it's one that's abandoned somewhere else that you didn't see, and there's cycling of water between aquifer systems and probably windows between aquitards that are allowing cycling to go through the units. I think overall the age dating tools are still relatively blunt. It's hard for us to say exactly what an age is in that sense, and it's probably a combination of mixing that's causing that. But people have found virus that are clearly indicated from being near surface in those deep systems as well, right through fractured aquitards. So it's phenomenal how we're learning about that cycling in the deep systems.
One last question?
Yeah.
Yeah, just it's an interesting subject. I worked on it's a project in perimeters 20 years ago. I noticed the past few years the European Union is powering some developments like to establish actually these perimeters in developing countries. And what about Canada? Is there some program that's trying to generalize the projects in perimeters around?
Like protection areas?
Yeah, around the water supply.
Yeah, so it isn't general. It's a province-by-province step. For instance, Quebec depends quite heavily on historical water quality in the production wells to define the vulnerability, whereas in Ontario, they've spent nearly $1 billion setting up models of all the watersheds throughout southern Ontario and trying to predict the capture zones. And of course, the capture zones are based on a steady state, non-changing flow field, which is is not the case at all. Of course, seasonality, the flow fields are changing. Add a well here and there, the whole thing changes, which makes the whole concept of a capture zone difficult.
Yeah, attracts your attention regarding inverting the
Flow field.
That was a paper that I published in the Wessex Institute of Technology
Yeah.
on 1980s.
Yeah, so I mean, the reverse technology flow has been around for a while, getting solute in the ground and trying to determine what breakthrough curves will be and getting more insight into it is, I think, a way that will help us.
Yeah, there's so many techniques that can be developed.
Excellent.
Thank you.
Thank you.